the talk, and we'll be talking about Arakelov random walks in Lattices.
Thank you, Daniele. Yes, so I'm very happy to give this talk. This is brand new slide for the first time. I'm not recycling any slide, so I'm very excited myself. Also, I think the result is quite interesting. So this is joint work with Wiskunde, Alice Pellemari, and Benjamin Wesolowski. So what is it about? It might be a bit cryptic like this. So it's a worst case to average case reduction from the ideal short vector problem to itself. And we do this by considering the space of all ideal lattices. And this is called the Arakelov class group. So it might resonate a little bit with a few things that had happened this week, where we were talking about the space of all lattices, SLN of R over SLN of Z. And basically, Arakelov class group is the equivalent of this space for ideal lattices. So what is exactly the result? Whoosh. So the Hermit VP problem. So first, I'm not doing exactly the shortest vector problem. I'm doing the Hermit variant of it. So this means that I'm not asking you to find a vector a short vector relatively to the shortest vector, but more in an absolute sense, more relatively to the volume of the lattice. And instead of having the root Hermit volume, the root volume in the equation, a simpler way of doing this is just assume that the volume of my lattice is 1, and this is going to be particularly nice in the setup of Arakelov theory. So, okay, you're given a lattice, it has volume 1, and you have to find a vector of length shorter than gamma. And our main result is that if you can do that over random ideal lattices in a particular ring, let's say. I don't want to go too much into number theory. I'm aware that you're just out of lunch. And also, I was asked to really go easy on you. I promise I'll do that. But Benjamin won't. So if you can do this for random ideal lattices, you can also do it for any ideal lattice over the same ring. And on the way, you're losing a little bit on the approximation factor, but actually not that much. Making the extended Riemann hypothesis and some other mild hypothesis, you can get this loss factor to about square root of n. Okay. So before I go into the details, how does it relate to the literature? Well, actually, there is, when we started working on the result, we said, oh, this is the first time in the lattice world where we reduce worst case to average case of the same problem, because sometimes you reduce ring LWE to ideal SVP, but this time this was the same problem, ideal SVP to ideal SVP, and we thought we were the first, but no, Damien told us. No, sorry, Leo. 10 years ago, Gentry already did it. But it's okay. So how does that result differ? It differs mostly in the way we define random. So Gentry kind of defined a rather ad hoc random distribution for his random case. I mean, it's not bad for cryptography. It's actually a distribution you can sample from. So he could build an FHE out of this distribution. But mathematically, it's maybe a bit frustrating as a distribution. We also reach, stronger reduction in terms of tightness, and we also don't need a factoring oracle to make it work. What's more interesting about this result is that it relates to recent development in cryptanalysis over ideal lattices. Those are the same tools that have been used by Damien Stellet and Alice Pellemari and their co-authors when they were working on the cryptanalysis of ideal lattices, maybe with some oracles. So basically, the lattice they constructed this morning, you can relate it to a lattice of relation over Arakelov class group. So Arakelov class group was actually hidden inside this talk, and I'm going to make it a bit more explicit during mine. And the last point that I find particularly interesting is that the strategy for the proof is exactly the same as the strategy that we've already seen in the world of elliptic curve-based cryptography. So somehow there was this result of Yao, Miller, and Venkatesan where they proved that the discrete logarithm problem was essentially as hard in every elliptic curve, was essentially as hard in any elliptic curve of isogeny graph, in an isogeny graph that in any of those curves. So again, I was told not to go too hard on the number theory, so I'm going to play a little game of taboo. So here are my 5 forbidden words: number field, embedding, Galois, exact sequence, and class group. Thank you. Noah accepted to play the referee. Okay, so I'm still going to need to define some, objects. So orders. So what are they? They're just discrete rings. And to get started, I'm just going to work with real quadratic orders with the principal ideal domain property. What does that mean? Well, that means that the class group is trivial. Thank you. Okay, so basically, I mean that one of my forbidden words is useless in this talk. Good. So what do they look like? By real quadratic, I mean that they are embedded into R2. So I want to construct a ring that is discrete inside R2. All right? And when I say R2, I mean R2 not just as a vector space, but R2 as a ring, where I have component-wise addition and component-wise multiplication. So, I mean, if I have a ring, a free, it has to be a free Z module. So I first need to put Z into it. And I really don't have a choice. For 1, I really have to map 1 to the coordinate 1, 1. Otherwise, it has to be a unit, so it needs to act as the unit on both axes. Otherwise, it's going to collapse to a one-dimensional thing. And then I need to choose a second point that makes it into a lattice, but also a ring. And that's where you need number theoretical magic. So I'm not going to tell you how it is done, but you're going to have to trust me that in this particular example is not only a lattice, but is also an order. You might, if you know number theory, you'll immediately recognize it. Okay, so now that I have an order, how do I construct an ideal? Well, I'm just going to multiply that order by an element from the space. So I choose an alpha in the embedding space. Sorry, in the ambient space. And I'm going to multiply each point of my order by this alpha, and I'm going to get an ideal. So I cannot always do this, but here I can do it because I assume the PID property. So this case is a bit boring. I just choose alpha equal 1, so my lattice is exactly the order. But then, of course, I can vary it, and whoosh, I get many different ideal lattices. All right. So if you remember, the first thing I did in this talk was to assume that the volume was 1, and here I just constructed a lattice for which the volume is not 1, or it's different from the original volume. So the first thing I can do is scale it back. And when I do this, I essentially constrain myself to choose alphas that lives on a hyperbola. So the hyperbola could also go down, but if I just multiply everything by -1, I can make sure that it is on the upper side of my plane. And then I can play with my alpha, but only on this hyperbola, and still get many different ideal lattices. And up to scaling, I get them all. That's essentially, it means that I do get all ideal lattices, but I just have to rescale them. I work modulo rescaling. I want to work modulo something else. I want to work modulo lattice that just looks alike. They're not exactly the same, but in terms of geometry, all the lengths and all the angles are going to be the same. So essentially, I'm going to call them the same, and I'm going to say that there's a symmetric group, and they're equivalent under this symmetric group. So basically, I can forget about the left part of my hyperbola and only focus on the right part. So now, to define an ideal lattices, all I have to do is to choose an alpha on the right segment of this hyperbola. So it means in some sense that I have parameterized the space of all ideal lattices by a hyperbola, and the hyperbola I can parameterize by a single real using this parametrization, for example. So now it means that, yeah, really, an ideal lattice is just given by a single real number that I'm going to call t. And by modifying this t, I get all the ideals associated with this order. But the thing is that it is not necessarily the case that all reals define different ideal lattices. And in fact, after a while, if I move t, I get the same ideal lattice again. And this is periodic. If I keep increasing it, I'm going to fall cyclically again on it again and again. So what I'm telling you is that essentially, if I want to parameterize the space of all ideal lattices, I don't even need the full line. I just need a segment. And really, this segment is kind of closed on itself. OK, so it's just a circle. The timing is not perfect. I need to work some more on it. So what did I tell you? I just told you that the space of all ideal lattices, maybe modulo those symmetries that we don't really care about, is just a circle.
One dimension, two dimension, and then...
Yes, for real quadratic orders. So to be...
Class number 1.
Pardon? Yes, real quadratic NPID. Class number 1. So this is something we summarize more pedantically by saying that the Arakelov is isomorphic to the torus of dimension 1. And this holds for orders that are real quadratic and have the principal ideal property. So the little, so PIC stands for Picard, the Picard group. And the 0 on top means that I'm working modulo renormalization. Okay, so because people take logarithms and stuff, the norm 1 translate to degree 0, whatever. So number theory. Yes, the Arakelov is the PIC 0 thingy. Okay. So what I just told you was for real quadratic PIDs, and I told you, so those are orders that I can, whose ambient space is R2, and for those, the Picard group is just a circle or a torus of dimension 1. So what happens if I remove this assumption? Let's remove the quadratic assumption. So now my order lives inside R to the R. And in that case, the Picard group is going to be a torus of dimension r minus 1. Why am I losing one dimension? Well, that's because of this renormalization property, right? So I get a torus as my Picard group. Now I'm going to remove the real assumption, and now it means that my order is lives inside r to the r times c to the c. And in which case, it's the Picard group is still going to be a torus, but a slightly bigger one. It has dimension t to the r plus c minus 1. So if you're thinking in terms of real dimension, you might have the feeling that I've stolen a few dimension, all of you, right? Because this space on top has dimension r plus 2c, but the thing on the bottom has just dimension r plus c minus 1. The thing is that those dimensions that have been lost to the symmetric group. Because when I put complex dimension, I kind of, I have a unit circle on each complex dimension that I can play symmetry with. So that's why I lose all those dimensions. And now let's remove the PID1, and that's where things get ugly, because then the torus get multiplied by the and we get a lot of we get a bunch of torus instead of a single one. So I should mention here that my direct product is only as only in a topological sense. In the group sense, it's not. You shouldn't do that. Okay. So why all this? Well, because I want to think of a reduction in this set. I want to relate ideal lattices to each other by thinking of how do I move to one ideal lattice to another in this set. And that's how I'm going to get a worst case to average case reduction. So I start from a worst case ideal lattice, and my little reduction here is going to randomly walk on the, come on, thank you. Is going to randomly walk over the Picard group to reach another lattice, and we're going to call this other lattice an average case lattice. Okay, and then once the reduction is here, she asks for a short vector, please. And reductions are French, are femal in French. Sorry, I said she, the reduction. The reduction is getting a short vector v in this average case lattice, and then the reduction is going to bring it back little by little to the worst case lattice by unwalking the original path. But at each step, you might notice that the vector v gets a little bigger. And in some sense, you don't want to make too long of a walk. The longer the walk, the biggest you're going to lose on the approximation factor. Okay, and when she's back on the worst case, she says, yeah, this is your short vector. All right. But what does it exactly mean to walk on this thing? Well, there are actually two ways of walking, and the first way of walking is very continuous. We've already kind of seen it. So I've parameterized my ideal lattices by a circle, and I can just move on this circle, which means I continuously transform my ideal lattice to another one. And here, I call my SVP oracle. I get a short vector of a certain radius inside a certain ball, and then I walk back, and by walking back, I'm distorting the space, and it means that the vector that originally lived in a ball now lives in an ellipsoid that is kind of distorted. So that's why it can get bigger. It does not necessarily get bigger, but in the worst case, it does get bigger. But that's just one way of walking on the Picard group. And if you just walk in this way, just the torus is just way too big. You're just going to distort way too much on your way back, and you're going to get a useless reduction. But there is another way of walking, and this time instead of doing distortion, I'm going to do sparsification. What does that mean? Well, there is kind of a way of teleporting myself from an ideal lattice to another one that is kind of related by just removing some of the points in that lattice. Okay, so come on, yes. So here I'm going to remove 1 point out of 2 in such a way that the new lattice is still an ideal lattice. So you need to be careful how to do this. Not all sparsification verifies this, but and then I get another related lattice. But you might notice that this one is not exactly on the Picard group because I've sparsified it. So its volume is not 1, so I need to scale it back. Okay? And now I'm on the Picard group. I can call my SVP oracle. And what do I do with the solution in that sphere? Well, I want to get back to my original lattice, so I need to undo the scaling. And then I just teleport back to the original point by undoing the sparsification. So here again, I've kind of increased the size of the vectors that I got when I undo this renormalization step. Okay, so I have two ways of walking, and now one is kind of discrete because there's not infinitely many ways of sparsifying a lattice. Even if you choose a fixed index, then there's only finitely many ways of sparsifying. And for ideal lattices, you have even more constraint. You cannot sparsify with any index. But by combining both, we're still going to be able to reach all points in the Arakelov. And so you should think of sparsification as just being discrete jump. And I start from a point, and from there I can reach, finitely many other points, but they're kind of randomly distributed over this continuous object. And because I'm only reaching a discrete set inside a continuous thing, I'm not reaching everything. So the sparsification is nice because it gets you pretty much everywhere for very little loss. But at the same time, you're really not reaching everything because you're discrete in a continuous set. And then there is the other kind of step, distortion steps, and those one are more the continuous walk that we've just seen. And when you're doing this, well, you're kind of blurring those dots. And the hope is that by having enough dots and by blurring them enough, you finally reach the uniform distribution. Thank you very much for your attention. I want to give a great thanks to 3blue19. So maybe you've seen his videos on the internet, and that's he made the tool that he used to do those his videos open source, and that's how I did my slides. And it's a lot of fun. It takes way too much time. Thank you very much. Any question before Benjamin drops in?
I think the questions are
Yeah, sure.
So, like, what kind of tools do you need to, like, control the statistical distance of the walk?
Is gonna.
All right.
Most of the questions are going to be answered by him, I guess. So.
I'm the only one who can answer because I'm not playing taboo. So I'm going to say class groups. I have the right to say class groups, and I'm going to abuse that right. Perfect. So I'm going to give the mathematical side of things. So I'm not going to talk about the worst case to average case reduction, but I'm going to talk about the random walks. How do you actually do the random walks, and how do we prove that they do converge to something that's uniformly distributed? I'm going to start with a simpler case, the case of class groups, which were treated maybe 15 years ago by Jao Miller and Venkat. And we use very similar techniques. So I'm going to walk you through this kind of simpler setting. So let's fix notations. We start with a class group, a number field K of degree n with ring of integers O. Its class group is simply the coefficient of these two groups. So the group of fractional ideals in the ring of integers O by the subgroup of principal ideals. Something very remarkable is that it's a finite group. The Arakelov class groups won't be finite groups, as you've already noted. So this makes the setting a little bit simpler. Just to fix notations, ideals are often going to be written like with these kinds of letters. The norm of the ideal is n of a, and the class of the ideal in the class group is written with square brackets. So to do random walks in these finite groups, we're going to use Cayley graphs. So what are Cayley graphs? They are graphs where the vertices are the elements of your group. So you can define Cayley graphs for arbitrary groups, but here I'm just going to work with finite groups. We get finite graphs, and more precisely class groups. So here every red dot represents an element in the class group. Alpha is one of these elements. Now you can pick an element in this group, or a representative for these elements. I'm going to use ideals as representatives for ideal classes. So choose an ideal L. Now, you can use this ideal L to multiply the elements in your class group. You can take this class alpha, multiply it by the class of L. You get another element in the class group, which is the class of L times alpha. And you add an edge to your graph when you do that. So you add an edge from alpha to L times alpha. You can do this from everywhere. You can keep going from there, and you go to L squared times alpha. You keep going, and at some point, you come back to where you started. Here you come back to where you started after 3 steps, which simply translates to the fact that the ideal L has order 3 in the class group. Okay. You can do this from anywhere in the graph. So in particular, you can also do this on these points you didn't reach, and you get another cycle, which is of the same length. Now this is with one ideal L. You can pick another one, say H, and do the same thing. So you go from alpha to H times alpha, and at some point you go back to the origin. Here after 2 steps, so H has order 2, and you do this with every point. This is a Cayley graph. So the vertices are elements in your group, and you've chosen a set S of ideals. I'm going to call that the generating set. And you add edges to your graph that correspond to multiplying by these elements in S. This is also a labeled graph because you have the green arrows which correspond to multiplication by L and the yellow arrows which correspond to multiplication by H. Okay? So now you can do, yes, question?
Yeah, it's a bit of a higher level question. So now you're talking about sort of randomizing the class, but I don't know, you could also think about randomizing inside the class, which I think is what sort of Leo's illustration was more, right? So let's say I only care about worst case to average case over principal ideals. Do things become simpler? Does it trivialize the problem? I mean, are these two parts disjoint from each other, or?
I'm going to talk during the second half of the presentation on how things change when you consider the full Arakelov class group, if that's your question.
So let's say I only cared about worst case to average case for principal ideals.
Okay.
So I don't care about randomizing the class.
Yeah.
Is it like easier than the general problem, or?
Well, I guess it's more difficult because this sparsification step will most likely transform principal things into non-principal things. So when you do your sparsification, you are restricted to sparsifications that preserve principality, and that might be.
Jump between classes.
Yeah, yeah. Okay, so to do random walks, we just follow random edges in this graph. So you start at some ideal class alpha. It's hard to compete with the previous presentation, but I do have little animations. So from alpha, you just pick at random an element in your generating set. So here it would be either L or H. So pick one at random, and you follow it. So from alpha, you go to H times alpha, just random. Then from H times alpha, maybe you go to L times H times alpha, etc. And you do as many steps as you want. And the question you're asking is, after making sufficiently many steps, do you end up uniformly distributed in there? So how fast do you become uniformly distributed? So how do we choose these generating sets? S, I said, okay, pick two ideals, H and L. In general, you're going to pick more than two. What you want is these ideals to have small algebraic norm, because the algebraic norm of the ideals you're going to use will affect the loss of approximation factor in your reduction. So you want ideals of small norm. To do so, you just fix a bound B, and you consider the generating set SB to be the set of all prime ideals of norm at most B. So these are going to be our generating sets, prime ideals of bounded norm. Now the question is, how large must B be for the graph to be well connected, for random walks to randomize fast? So first, how large must B be for the graph to be even connected? If it's not connected, you're not going to have random walks that become uniform because you're always going to be stuck in a connected component. So you start with just the vertices of your graph, and you can start slowly adding ideals of increasing norms. Maybe first you add all the ideals of norm 2, and you get something like this. It's not connected yet. Maybe you go to norm 3, and you get something like this. OK, it becomes connected. That was too easy. But we do have general bounds. Eric Bach proved in 1990 that choosing B to be 12 times the logarithm of the field squared, then you always obtain a connected graph. Connected. Not necessarily well connected. You don't know how random walks happen in these graphs if you just pick this bound. It could be think about like an enormous cycle. It's connected, but it's not well connected. If you do a random walk in an enormous cycle, you're probably going to take a while before reaching the other end of the cycle with a simple random walk. OK, but we can add more edges. We don't have to stop at this bound and get better connectivity. To study that, one can use a classic object of a graph theory called the adjacency operator. The adjacency operator, it's an operator on the set of functions from the vertices of your graph to the complex numbers. So if you're given a function like this, here are the vertices of our graph of the class group, so a function from the class group to the complex numbers. The adjacency operator is defined like this. The adjacency operator applied to f, evaluated at any point alpha, is the average value of f at all the predecessors of alpha in the class group. So you take f, you evaluate it at all the predecessors of alpha, so alpha times the inverse of your generating set elements, and you take the average of that. So why do we do this? If f is a probability distribution over the class group, Then applying n times the adjacency operator to f gives you the corresponding distribution after you've done n steps of the random walk. Okay. So now you need to study this operator and see how it acts on this space of functions from the class group to the complex numbers. And the question you're trying to answer is, if you pick any starting function f, does it converge to something, or distribution f, does it converge to uniform, and how fast? To study this question, one can resort to Fourier analysis for finite groups. You know that the characters, so characters are group homomorphism from your starting group to the multiplicative group of the complex field. These characters, they form an orthogonal basis of the space of functions from the group to the complex numbers. And what's extremely convenient is that these characters, not only they form an orthogonal basis, but they also form an orthogonal basis of eigenvectors for the adjacency operator. And this is very simple. Just pick your operator, apply it to your character, and see what's happening. This is just the definition. Here you can split this multiplication because the characters are homomorphisms. Just get that. This doesn't depend on p, so you can just write this to be lambda chi. So this is the eigenvalue of the eigenvector chi. Okay? Now it's very easy to see that if you pick the trivial character, which I write 1, the corresponding eigenvalue is just 1. And if you take any other character, then the eigenvalue is at most 1. So, as I said, the characters form an orthogonal basis. So you can take your function f, you write it as a linear combination of the characters, and you can apply the adjacency operator to this. It's a linear operator, so you can apply to each component individually. Since the trivial eigenvalue is 1, it leaves the component corresponding to the trivial character untouched. And all the other components, well, you just get the eigenvalues to the power n multiplied by whatever you had. Okay? So now, if you imagine that all the non-trivial eigenvalues are strictly less than 1, then this will tend to a1 times the trivial character. If f is if f is a distribution on the class group, then a1 is 1 over the class number, and a1 times 1 is the uniform distribution over the class group. So you just need to prove that all the eigenvalues are strictly less than 1. And that's what Jerome and Venkat did in 2005. They proved that you can choose a bound B and the corresponding generating set of all prime ideals of norm at most B, such that all the non-trivial eigenvalues are small enough. The non-trivial eigenvalues being small enough mean that all their nth power rapidly tend to 0 as n tends to infinity, and therefore the random walks rapidly tend to uniform. Okay? Yes?
Like, how many of them are there?
How many what?
How many, how big would like SB be? Like, is it gigantic or?
No, well, it's polynomial size. You can actually sample uniformly in there. Pick a random prime, factor it, pick a random factor. You have to be a little bit careful in your distribution if you want it to be uniform over all the primes, depending on how it splits.
All of them of norm at most B, or do you just pick some of them at random?
At each step, you need to pick one.
Ah, okay. For the, yes, I see what you mean. Yes, you can like, you don't have to like build a huge list, you just sample for one.
Yeah. Okay, so they used this to prove the random self-reducibility of the discrete logarithm problem on elliptic. Oh, you had a question also.
Yeah, just why do they care about the norm in the context of discrete log, right? I mean, for short vectors, I understand.
Yeah. So I'm coming to that. So they proved this for the random self-reducibility of the discrete logarithm by showing that these Cayley graphs that I show, they correspond to isogeny graphs. So graphs where the vertices are elliptic curves and the edges represent morphisms between them. And the algebraic norm of the ideals that you use correspond to the degree of the isogenies, of the homomorphisms. And the algorithms to compute these isogenies are polynomial time in their degree. So if you want to actually be able to transfer the discrete logarithm, you need to evaluate these isotonies, and therefore you need the degree to be not too large. Now let's go to Arakelov class groups. So I'm going to start by actually defining it. And the definition is extremely similar to the definition of a class group. So the class group was just the quotient of the group of fractional ideals by the subgroup of principal ideals. Now, principal ideals, you can see them as just the direct sum indexed by all prime ideals of copies of Z. This isomorphism, it's just the factorization of ideal morphism. So given an ideal A lives in there, you can factor it as a product of prime ideals, and you write its factorization as a vector like this, where each coordinate indexed at P is the valuation at P of the ideal A. So this is a vector of integers where you have zeros almost everywhere, except at the places, at the primes that divide P, that divide A, sorry.
Are we assuming the ID here?
No?
You say principal instead of saying all ideals.
Ah, okay, I heard principle.
Oh, okay. So yeah, this is just the factorization of A. And the class group, you can see it as this direct sum of copies of Z quotiented by the factorization of the principal ideals. Now, an observation is that prime ideals, they are just the so-called finite places of K. So I'm not going to go into details of what places are, but essentially a place of a number field is a way to define an absolute value in your number field. And you have two kinds of places: the finite places, which are precisely the prime ideals in your number field, and another family of infinite places, which are essentially the embeddings of your field into the complex numbers. Essentially because you're going to want to work up to conjugation. So an embedding of your field into the complex numbers up to conjugation. And we call these the infinite places. So it's not probably immediately obvious how these embeddings relate to prime ideals, but that's you would need to go into details of what places exactly are. But we can still use these definitions to define the Arakelov class group. So again, the class group is this quotient. And we can extend this sum with a part that takes into account the infinite places. So here it was the sum of copies of Z over all the finite places, the prime ideals. Now you take the same thing, but you add copies of the real numbers indexed by the infinite places new. Yeah?
You don't have unique factorizations in orders in general. How are you doing this?
Sorry, what was that?
You don't have unique factorization in orders in general. So how are you doing this direct sum with Z now?
You don't need unique. You have unique factorizations of ideals. That's all you need.
Integers.
Yes. Okay. Now, to define the class group, you needed a notion of principal ideal. And the principal ideals were exactly the image of the multiplicative group of your field into this direct sum that sends an element x to the factorization of the ideal generated by x. Yeah? And the class group is just the co-kernel of this map, so the range quotiented by the image. Now on the side of divisors, you also need a notion of principal divisor. And you can define this in a very similar way as the image of k star of some morphism. So you can take an element in k star x and send it into this direct sum by first taking, well, exactly the same thing as you had here. So the prime factorization of the ideal generated by x, and adding this quantity here, which some of you might recognize as the logarithmic embedding. And now you can define the Picard group in the same way as the co-kernel of this map. So this direct sum quotiented by the image of k star.
Did you tell us what nu
We are summing over all the infinite places, so the embeddings of the field into the complex numbers up to conjugacy.
Okay, so it's an embedding.
Yes. So that's the Picard group. It's not yet the Arakelov class group. The Picard group has a so-called degree 0 part. Leo told you it corresponds to rescaling everything so that everything has norm 1. And that's why you have a 0, because the log of 1 is 0. And that is what we call the Arakelov class group. That is what we call the Arakelov class group, because depending on which article you're reading, sometimes this is also the Arakelov class group. And it relates very simply to the Picard group. So the Picard group is the direct product of this degree 0 part by R. This is just the rescaling part. What's very convenient is that this degree 0 part is compact, whereas this is not. Now here's a nice exact sequence. Here you have the degree 0 of the Picard group. This morphism to the class group is just the morphism that forgets about all these infinite places. So if you have an element in there, you can just forget about all these components, and you fall into exactly the class group. And this is this morphism. It is a surjective morphism. You can reach everything in the class group like this. It is, of course, not an isomorphism, because this is infinite and this is not. It has a kernel. And the kernel is this T here. And this T is the torus. So the class group, it's a finite group. It's, in some sense, the discrete part of what's happening in the Picard group, in the Arakelov class group, sorry. This T is the unit torus. It's somehow the continuous part. It's infinite, but it's compact, and it's connected. And the Picard group sits in the middle. It's a bunch of copies of this torus. Essentially, you pick every point in the class group, and you replace it by a torus, and you get the Picard group. So from this exact sequence, you do get this idea that the Picard group is the direct product of this class group by the torus. But that's only true topologically, as Leo said it. Algebraically, well, it's almost a direct product, but not quite. All you can say is you have an exact sequence like this. Okay. Now we're ready to do discrete random walks. So let's do something that's extremely similar to what we did in class groups. Say you start somewhere in the Picard group. So you sit somewhere in one of these tori. You can try and start doing the same thing. We let SB be the set of all prime ideals of norms smaller than B. Now, prime ideals, they are not elements in the Picard group. What you could do is look at their class, and then you would get something in the class group, but you don't get quite something in the Picard group. You need to choose representatives for them in the Picard group. So if you pick a prime ideal P in SB, you can look at its class. It would be, for instance, this point. And you need to choose a representative of this class in the Picard group, namely a preimage under this morphism. So you do this, and you call it D of P. There's a canonical way to do this. And then once you have that, your random walk is just the same as we did for class groups. You start somewhere, and you multiply by random D of P's for P taken from this generating set. Yeah? So this corresponds to the sparsification walk that Leo talked about. Oh, yeah, question.
Does it matter which point on the donut that we're choosing for regarding the distortion that we take? Or?
I think it doesn't strongly matter. Your choices should be compatible with each other. You mean which preimage we pick? Or could we pick this one instead of this one, as long as it's in the same torus? You could do different choices, and it would work.
Does it have any effect on the distortion and so forth that you're...
No. No. So we choose to do it in a very canonical way. I'm not sure exactly what would happen if we don't, but I think it would be the same. Yeah. So we can study that, these discrete walks, using something very similar to the adjacency operator called the Hecke operator. It's pretty much the same thing, except you write stuff additively instead of multiplicatively, and you work with Picard groups or Arakelov class groups instead of class groups. So the Hecke operator is an operator from the space of functions, on the space of functions of your Picard group. It takes as input a function f from the Picard group to the complex numbers. So exactly the same situation as previously. And is defined as follows. So for any element A in the Picard group, applying the Hecke operator on f and evaluating it at alpha is just taking the average value of f at all the predecessors of alpha. So this time, the predecessors of alpha, they are not alpha divided by the class of P. They are alpha minus the chosen representative of P. And now the question we're trying to answer is, does applying n times this Hecke operator to a function f converge to uniform for any initial f? And how fast?
Is there a continuous aspect to this operator, or this is? Like
Yeah, not yet. The continuous aspect will come from your choice of f. If f is, say, a discrete function, something that's 0 everywhere except at a few points, then you cannot hope for this to converge to something uniform. So we can try to do exactly the same thing. We do have some Fourier theory for Picard groups. They are compact groups, the commutative groups even, and the space of all characters, which are also defined in the same way. The homomorphisms from the group to the multiplicative group of the complex numbers. They form an orthogonal basis of the space of functions of the group. And they are also eigenvectors for the Hecke operator, just like the characters were eigenvectors for the adjacency operator. The proof is exactly the same, and you get something like that with eigenvalues that are exactly the same, except there's a typo here. It shouldn't be the class of D, but D of P, the chosen representative. Now we still have that the eigenvalue associated to the trivial character is 1, and all the other eigenvalues are at most 1. And we can ask the same question. We decompose f as a character sum, and we can apply the Hecke operator n times, so this should be an h. And you get this decomposition, and if all the non-trivial eigenvalues are sufficiently smaller than 1, then this will tend to the uniform distribution as n grows. Yes?
But do you not have like infinite characters?
Yes, you do.
Okay.
Yeah.
So, but then that has to be quite carefully quantified.
Yes. So let's be a little bit more careful and see what's all the precise statements. So we can prove, assuming the extended Riemann hypothesis for Hecke characters, that the following holds. There is a bound B, so B is the bound on all the norms of prime ideals you consider, such that for any non-trivial character, the eigenvalue is at most this quantity. So what do we have in this quantity? We have in the numerator some logarithmic value, some logarithmic quantity in B, and in the denominator some square root of B. So in B, the denominator grows much faster, so it seems you can always choose B to be such that the denominator is much larger than the numerator, and you're going to have something that's very much smaller than 1. Except you have this quantity here also in the numerator, which is, it's called the infinite part of the analytic conductor of the character. You can think about it essentially as the frequency of the character. It's how fast does the character oscillates. So this bound, for characters that have a very high frequency, will not be so good. It won't tell you much. It might even be, I mean, the bound might be larger than 1, which you know is impossible for eigenvalues. So this is a void bound when the analytic conductor is too large. Okay, but we still have something. The eigenvalues are small for all the non-trivial characters, as long as the frequency is not too high. So applying your random walk will quickly annihilate all the components that come from small frequency characters. Now what do we do with high frequency characters? That's where we need the continuous part of the random walk. You add a small continuous random walk to annihilate the high frequencies. For that, you use a Gaussian with a chosen standard deviation S. And you're going to need to see how big must S be for the high frequencies to be annihilated. So once we take this into account, we get the final result. Pick any standard deviation S for your discrete part of the random walk, and any epsilon. Then there is a bound B on the norms of the ideals we're going to have to consider. This bound is polynomial in all these quantities, such that for any random walk where the discrete part has a length at least this quantity, then the endpoint of the random walk, so the discrete random walk plus the continuous random walk, is at statistical distance at most epsilon from the uniform distribution.
Is delta the discriminant of the field?
Yes, sorry, delta is the discriminant of the field. So that's the theorem we can prove using this Fourier analysis. And that concludes my talk. Any questions?
Can you say again what is dp in your notation?
Say what?
D alpha or dp? The slide before.
Oh, dp. This dp?
Yeah, dp, yes.
Okay. Here, you want to choose how you're going to take steps for your random walk. And a step in the random walk is multiplying by something chosen from a finite set. That's the discrete random walk. So you need to choose this finite set, the so-called generating set in the first setting. So we do this by picking all the prime ideals of norm at most B. But picking just prime ideals don't give you canonically a point on these objects. They only give you canonically a point in the class group. So that would be, for instance, this point. Now you need to make a choice for a preimage of that. And this is dp.
So is that just the inverse of the one?
So yeah, the inverse of the point would be the whole torus. And you have to make a choice and say, I want that particular point on the torus.
How do you parameterize? I mean, Leo mentioned something, but how do you parameterize this torus in generality? Like, what is it? Something you can mod out by something in units, or what do you do exactly?
Yeah, so it's you consider the logarithmic embedding, which goes to r to the power of the number of real embeddings plus the number of complex embeddings minus 1. And the logarithmic embedding of your maximal order is a lattice in there. And this torus is the quotient of your space by the lattice.
The degree 0. So you need the relation that sum function.
Yes, yes.
That's why dimension -1.
Yes, exactly, yeah. Yes?
Why are you choosing it? What's the difference between DT and P? It's only at the level of prime ideals because it only differs by a unit, so it's actually the same prime ideals.
I didn't get that.
Between DT and P as prime ideals, what is that?
The difference between dp and p? dp is not a prime ideal. It's
DP as an ideal in the geometry?
No, it has two parts. It has the finite part, an ideal, and the infinite part is some vector in Rn. So the infinite part is the one he mentioned before. So it's not an ideal.
But doesn't the infinite part correspond
The
to
infinite
the
part
units?
is an ideal, the same class as P.
But
So-
doesn't the infinite part correspond to the units?
the finite part, the infinite part corresponds to the units. That's your question? Yeah, well, this part corresponds to the unit torus that you see in the, but it's
some vector in Rn. Just think like you have n components of a vector. That's it.
This part gets quotiented by
It's modular the log unit.
it's not the units. It's the ambient space quotiented by the lattice, the logarithmic units.
Is it quotient by the units log units or log units? Position, all these,
So the quotient is by, where am I defining that?
The key in your notation is you take the Rn space with degree 0 and take the quotient with the log unit.
With the log units, yes.
So these are just units.
Yeah. Yes.
So this, what you call SP is roughly B over log B, the size of this is.
What I call SB is, yeah.
So does the Riemann hypothesis part comes from the fact that the error term of this assumption is as small as the smallest possible?
So the Riemann hypothesis comes from the estimation of the character sums. So the yes. So the eigenvalues that we get are of this form. So we get character sums. And then assuming the Riemann hypothesis for the Hecke-L functions, you get an estimation of this sum up to an error. And the precision of this error relies on the Riemann hypothesis. Yes?
So it's related to my previous question about choosing the point on the donut.
Yeah.
Does the choice of point have any effect on the step in the random walk? I don't see how there's any dependence there. Because the step on the random walk is it merely sparsifying by this prime ideal, or something additional?
Is it?
The step on the random walk,
Yes.
whole space, is it merely just sparsifying the ideal by the prime ideal that you've selected, or is there something more going on corresponding to the infinite places in that step in just one step of the random walk?
It's just the sparsification. Yes.
So I guess my part I'm confused. I'm fearing I'm missing something, but maybe I'm not. The choice of D of P, where you have to kind of just choose some values for the.
Yeah, I see what you mean. Yeah.
Have any effect on the actual step of the random walk, or what?
It does not affect the random walk. It's just a way to analyze the thing. I mean, the walk is happening without this
Right, that's
pullback happening.
I think
so
that's what I'm confused about.
It's
just for the analysis.
it's really just an arbitrary choice to think about it.
For the analysis. Okay.
Yeah.
It's not necessarily well defined, but like the rapid mixing of the properties of the discrete walk in the Cayley graph of the class group, this was already known by your prior work. And here I have the feeling that there's like a discrete walk and a continuous walk. So could we say like this is maybe more of a result on the continuous walk? Like could this be like I mean could the focus be only on the continuous walk to obtain that result, or do you
I guess you can deduce.
structure to prove
If you separate those, you get some very terrible bounds.
Yeah.
it's bad? So you really have to have it somehow in one
Yes.
class group, as opposed to just looking
You.
at
I guess you wouldn't get something good if you were doing the random walks on the torus independently and then trying to combine that with the previous result on random walks on the class group.
Yeah.
Yeah.